2.7, inverse functions. A lot of the things that we do with inverse functions kind of relates to composition of functions. We're going to use a composition of functions to determine if, in fact, two functions are inverses. We're going to find inverses of functions. And I think we've done this before. Do you remember having a set of points and asking what's the inverse? If I had a set of points and I give them to you, how do you find the inverse? Do y'all remember? Huh? No. No. Swap the x's and y's. Do you remember doing that? So I give you a set of points. If you swap the x's and the y's, that's the inverse. Okay. So we're going to do that with equations, though. We're going to talk about one-to-one functions. I don't think we've talked about one-to-one before, have we? Y'all recall me ever talking about a horizontal line test? We've done vertical line tests, but how about horizontal? Okay. So horizontal line test is going to be used. We're going to talk about one-to-one functions, and then we're going to use algebra to find inverses. So that's what we're doing in 2.7. Quite a bit going on, but it's really not all that difficult. So we know that a set of ordered pairs can represent a function. If the x's don't repeat, right? If the x's don't repeat, we have a function. So here is a set of points. 1, 2, 3, 4. That's my a values. If I take the values 1, 2, 3, and 4 and plug them into this function, f of x is equal to x plus 4, I would get 4 output values, right? Plug a 1 in, I get 5. 2 plus 4 is 6. 3 plus 4 is 7, right? No big deal. So by doing that, by plugging those 4 numbers in, from the function x plus 4, I end up with function 1, 5, 2, 6, 3, 7, and 4, 8. Still a function. So now if we were to take each of these values and swap them, making it 5, 1, 6, 2, 7, 3, and 8, 4, that would be the inverse for that set of points. We denote inverse by using an exponent of -1. In the past, when you've seen an exponent of -1, we referred that to as a reciprocal, right? Y'all remember doing that? If I had 2 to the -1 power, we would say, well, that's just 1/2. Okay. But since we're talking about functions here, it is not 1 over that function. That's not how this works. So when you see an exponent of like that -1, this is read f inverse. Okay, f inverse. So going back to the function that we started with, our function was 1, 5, 2, 6, 3, 7, and 4, 8. That was f of x. F inverse of x is those 4 points reversed. 5, 1, 6, 2, 7, 3, 8, 4. Okay? So let's think about this. If I'm swapping x and y, x is our domain, correct? And y is range. Well, if the function has a specific domain and we're swapping the x and the y, that domain becomes the range of the inverse. The range of the original function is the domain of the inverse. Did y'all follow that? If we're switching x's and y's, then domains and ranges are swapping as well. And that's what this is talking about right here. Okay, now they don't go into a lot of detail on this part, so I want to redo this. And we're going to do this again here in a little bit. It says, in other words, when you form the composition f with f inverse, or the composition of f inverse with f, you obtain the identity function. Okay, where did that come from? I think they skipped a lot of concepts and steps here. So my original function was f of x equals x plus 4, correct? That was the original function. F of x, what's another way of saying f of x? Y. So this is the same thing as saying y equals x plus 4. So when I'm trying to find the inverse of a function, let's go ahead and write them as x's and y's and not function notation. Okay. I'm going to change colors here because we're going to go to inverse now. Step number 1 in finding inverse is swap the x and the y. So this y becomes x x becomes y. I want y by itself. What does y equal? X minus 4. Okay? But y can't be x minus 4 because y is x plus 4. So this isn't really y. This is really, that's a 1. This is really the inverse function. Now, I don't want you to think that all you have to do in a function is change the constant sign and now you have the inverse. That's not how it works. That's just how it happens to work on this one. So how do I determine if two functions are inverses? Well, if I do a composition of f with f inverse, meaning what is f, go back to the blue. What is f of f inverse of x? That means take the f function. So my f function was, or is, my f function is x plus 4. But I'm not going to write an x, right? In place of x, I'm going to write x minus 4. So in place of x, I'm going to write x minus 4. Let's finish the f function plus 4. What happens when you simplify that? X. Okay. What does the line y equals x look like? Right through the origin, 45°, slope of 1, y-intercept is 0. Okay. The line y equals x is called the identity function, right? You give me an x value, I tell you what y is, and it happens to be the same because it's identity. Okay. To determine if two functions are inverses or not, you have to check it both ways. You have to plug the inverse into the original function. You also have to plug the original function into the inverse. So not only do I want to know f of f inverse, I want to know what is f inverse of f of x, which means take the inverse, and I'm claiming this is the inverse. We did the math. The inverse is x minus 4. So in place of x, I'm going to put x plus 4. Now let's finish writing the inverse function. It's x minus 4, so I need minus 4. Simplify that, what do you get? Okay. It is possible that if you plug in the inverse, you get x, but when you plug in the function itself, you get something else, or vice versa. You must get x both ways for them to be in fact inverses. Questions on that? Questions on anything related to this class and this course and this topic? Okay. Had to shut Allison down before she got started. Okay. Here's a problem that's already worked out, but we'll work it again. It says find the inverse of f of x equals 4x. Then verify that you did the math right. That's what it says, right? So f of x is 4x. How do I find the inverse? Y equals 4x. Now what? Swap your x and your y. I like what you said better. Swap your variables. Sometimes an equation might not be x's and y's. Okay. So in this case, we swap the x's and the y's. So I have x equals 4y. Let's get y by itself. X divided by 4. Okay. Which is the inverse. Supposedly. Okay, so step number 1 of this problem was to find the inverse. We claim this is the inverse. Now let's verify it. To verify it, we have to do the composite functions both ways. So I want f of f inverse of x, which means take the original f function, which is 4x. But in place of x, we're going to plug something in. What are we going to plug into that? X over 4. What is 4 times x over 4? The 4's cancel, leaving us with x. So the first half looks good, but we have to check it both ways. What is f inverse of f of x? Meaning, take what we claim to be the inverse function. In place of x, we're going to plug something in. So the x is in the numerator. I've got a 4 in the denominator. My original function is 4x. So in place of that x, I'm going to place a 4x. Does that simplify? The 4's cancel, we get x. So because I got x both ways, I have in fact verified that my calculation of the inverse is in fact the inverse of the original function. How are we doing? Again, for the third time. All right, so they're going to go ahead and do it. There you go. They plugged it in just like we did. Moving on. Definition of an inverse function. Let f and g be two functions such that f of g is x and g of f of x. If that is true, if f of g equals g of f, which is equal to x, then f and g are in fact inverses. And again, it's denoted f inverse. That's how this is read. This last statement here, the domain of f must equal the range of the inverse. That's what I talked about a while ago. The domain of the function is the range of the inverse. The range of the function is the domain of the inverse because x's and y's swap. I talked about this already. That -1's exponent does not mean reciprocal, so don't go there. That -1 is referred to as the inverse. If the function g is the inverse function of f, then f must be the inverse of g. So we would simply say f and g are inverses of each other. Anytime you have inverse functions, if you're looking at a graph, inverse functions, you can tell that they're inverses or not if they are symmetric about the line y equals x. And you see on this graph, you see the dotted line, that's a y equals x. And notice the dark line and the line above it do appear to be symmetric about that line. So because those two functions are symmetric about the line y equals x, those two functions are in fact inverses. And this is going to always be true. Okay, this problem says sketch the graphs of the inverse functions f of x equals 2x minus 3 and f inverse is equal to 1/2 of x plus 3. They are telling us that these two functions are inverses. I'm not going to sketch them as far as on paper. I will sketch them using the calculator. Nice. Okay. So to graph these, I will enter into y1, I'll graph 2x minus 3. And in y2, they're telling us that it is 1/2 of x plus 3. So 1/2 of x plus 3. Okay with that? And now just for the heck of it, I don't have to do this, but I'm going to go ahead and change y3 to be y equals x as a dotted line. Okay, so I'm going to come down here to y3. I'm going to change this to a dotted line like that. And I'm going to make this function y equals x. So when I graph these, it should be symmetric about that line. So I will go zoom square to keep everything nice and square both directions. What do you think? Does the red line and the blue line look symmetric about the dotted line? Could I fold it in half on that dotted line and they lay on top of each other? Looks like it. Okay, we might have some skewing issues or whatever, but yeah, that's how it would look. Okay. And I'll go back to the slideshow here and go to this next slide, and here those graphs are. And there's the dotted line in between, and you can see that they are symmetric about that line. Therefore, those two functions are in fact inverses. It would not look like you could fold it in half. They don't have to be lines. This dotted line has to be a line, but the functions on the other side don't have to be. These are the same two graphs. If we were to go and look at the tables on these graphs, we would see that -1, -5 is a solution to f of x. And if I swapped x and y, -5, -1 would be a solution to the inverse. And that's going to be true for every point. And you can see that on the calculator. If I go to my table, if 1 goes to -1, then for this graph, shouldn't -1 go to 1? If we switched them, -1 goes to 1. Okay, so -1, 1 is a point on y2. 1, -1 is a point on y1. They gave us -1, 5. So -1, -5 was a point like they showed us on the graph, which means I should see a -5, -1, right? -5, -1. Okay. So again, they just shown some points, just a few random points to show you what's going on there. The reflected property of the graphs of inverses give you a nice geometric test for determining whether a function has an inverse function. The test is called the horizontal line test. If a graph fails the horizontal line test does not have an inverse. A function has an inverse function. What does the phrase if and only if really mean? This thing says a function f has an inverse function if and only if no horizontal line intersects the graph of f more than one point. Okay. Do you remember how I abbreviate if and only if? If I ever write those three letters, that means if and only if. Okay. If you see the phrase if and only if, it means you could read the sentence forward and backwards, and it's the same, it's a true statement. For example, and let's ignore the fact that Fox rains exist. Y'all know what a Fox rain is? A Fox rain, it's like if you were to walk out right now and all of a sudden there was rain. I mean, do you see any clouds out there? So typically it's not going to rain right now, right? But a Fox rain is when there's actually rain that occurs when there's no clouds. That's called a Fox rain. But generally speaking, okay, so I'm kind of lie a little bit here. If I was to say it rains if and only if it's cloudy. Okay. Can I say that the other way? It's cloudy if and only if it rains. You see a problem? Okay. So we can't do that, can we? Okay. So if and only if means that it would be a true statement whether you went forwards or backwards. So this says a function has an inverse if and only if no horizontal line intersects the graph at f at any one point. I could also say no horizontal line intersects the graph of f at more than one point if and only if the function of f has an inverse. Okay. So if f of x was x squared, is an inverse? Why not? Okay. This function is a parabola like this, correct? Does that fail the horizontal line test? I'm going to be tricky on you now. If f of x equals x squared with a domain of x being greater than or equal to 0, is there an inverse? Why? Yeah, folks, this graph here would look like that. Does that pass a horizontal line test? Yes. Does it pass a vertical line test? Yes, it's a function, right? So this, both of these, f of x equals x squared for x being greater than or equal to 0, that's a function. F of x equals x squared, that's a function. The red one does not have an inverse because the entire domain, it fails the horizontal line test. If I restrict the domain of x squared to being x is non-negative, this does have an inverse. And the inverse would look like this. Does that appear to be symmetric about the line y equals x? What is that equation? It's the square root of x. Okay? Those are inverses. Let's check it. What's the square root of x squared? X. What is the square root of x squared? X. Okay? If no horizontal line intersects the graph at f at more than one point, then no y value is matched with more than one x value. This is the essential characteristics of what we call a one-to-one function. So for a function to be one-to-one, it must pass the horizontal and the vertical line test. If a function passes the horizontal and the vertical line test, that function is said to be one-to-one, meaning every x has exactly one y, and that y only has that x. Okay, no repeats. A function f is one-to-one when each value of the dependent variable corresponds to exactly one value of the independent value, which is exactly what I just said. A function f has an inverse function if and only if it's one-to-one. I've stated that before. A function must be one-to-one to have an inverse. Okay. They're going to talk more about the x squared, which I've already talked about in quite detail. If I took the function x squared, here are some x values with the corresponding y values. If I swap x and y's, I could graph that, couldn't I? I could swap x and y's and graph it, yes? Yeah, I could do that. And this is what it would look like. Is this one-to-one? I've got stuff that repeats, right? Because I have stuff that repeats, it can't be one-to-one. There's other stuff that repeats. The ones repeat. Okay. Says the table on the right does not represent a function because the input x equals 4 is matched with two different outputs, -2 and +2. So f of x equals x squared is not one-to-one and does not have an inverse function unless you restrict the domain. Then I have a different function. Does this graph pass horizontal and vertical line tests? Yes. Does this function have an inverse? No. Yes. Does it pass horizontal and vertical? Yes, which makes it one-to-one. So if it's one-to-one, does it have an inverse? Yes. And we could find the inverse. If I was to write y equals x cubed. Back up. Let's find the inverse. Swap x and y. Get y by itself. What would we do? Add 1. Y cubed equals x plus 1. Now what? Now do the cube root of both sides. Y equals the cubed root of x plus 1. And if I took those and put them in my calculator, clear this guy out and clear this guy out. My original function was x cubed minus 1. And then I have the cubed root of x plus 1. And my dotted line there. What do you think? Does that look symmetric? Okay, yeah, you could fold it right across this line right here. It looks nice. Okay, here's x squared minus 1. Does it have an inverse? No, because fails horizontal line test. If the functions are simple, you can find inverse functions by just inspection. For more complicated functions, you use the following guidelines. They're about to list the steps of solving for the inverse. They put a couple extra things in there that I've kind of talked about. They're saying that step 3 is where you swap your x and the y. How you number them is not that important. First thing you need to do, does it pass a horizontal line test? If it passes a horizontal line test, let's see if we can go ahead and find the inverse. If it fails a horizontal line test, don't spend your time doing it. There's no inverse. Okay. Step number 2, replace f of x with y. Step number 3, swap the x and the y. Step number 4, solve for y. Or they're solving for f inverse. I'm not going to do it this way. I'm not going to replace the y. I'm sorry, I'm not going to replace x's with f inverse of x. That's just a lot of writing, especially if you had like an x and an x squared and all kinds of messing going on in there. That could be very sloppy. So just working with y is a lot easier. Notice what I'm doing, and I change colors, don't I? When I swap x and y, that's to remind myself, look, these are different x's and y's. So when I get done, I need to fix it. And that's why I change the y to f inverse when I get done. Okay. So there's just the steps of doing it. We're going to work this problem. Do not look at the notes on this problem because they messed up so bad. We're not even going to look at them. We looked at it during the second period. I don't know what they were doing. So let's find the inverse. So to find the inverse, the first thing I'll do is change f of x to y. So y equals 5 minus 3x divided by 2. Swap x and y. X equals 5 minus 3y over 2. Let's solve for my new y. What do I do first? Multiply both sides by 2 gives me 2x equals 5 minus 3y. Next step. Subtract 5. 2x minus 5 is equal to negative 3y. Next step. Divide by negative 3. I'm going to switch it around. Y equals 2x minus 5 over negative 3. Technically, this is correct. I don't like having a negative number in the denominator. So if I multiply the top and the bottom by -1, is that legal? Okay, I can multiply top and bottom by -1. So -1 over -1, which means y is -2x plus 5 divided by 3. So since we're saying that this is the inverse, I'm going to write this as f inverse of x is -2x plus 5 over 3. We can check that by plugging the f function into the inverse and then plugging the inverse into the f function to make sure we get what we wanted. We could also graph both f of x and f inverse of x on the same plane, and you would see, if I drew a line, that's nice. If I drew the line y equals x, it would reflect through there. Okay, I'm not going to mess with doing that right now. Questions on that? Okay. Don't look at this or this because they made a mess, and that's it for 2-7. Okay.